Hamiltonian with the driven harmonic oscillator. Remember the Hamiltonian looked like this. We introduced the variable A of t incorporates the information about both Q and P, the canonical, the pair of canonical variables. This was basically P squared over 2 plus omega squared half Q squared of t, and that was the driving force Q of t times J of t. We found, by solving the quantum mechanical problem, that the Hamiltonian has the following solution. It is a constant operator for early times before the force starts acting at t equals 0. Then it's something more complicated while the force is acting, and then after the force is done with acting, it's again a constant operator. That is to say, it's this constant operator for all times larger than capital T, which is when the force stopped acting. Here the definition is that A in is the operator A of t evaluated at t equals 0. A out is the operator A of t evaluated at A of capital T. And we found that A out is related to A in this way. A out is A in plus J naught. And J naught is the identity operator times this integral here. We proceeded by diagonalizing the Hamiltonian for early times. We said, well, at early times, the Hamiltonian is this constant operator in Hilbert space, which we may also call H index t smaller 0. It's self-adjoint and it's constant, so it's inviting to use its eigenbasis to expand states early on in the quantum evolution. And to this end, we used the fact that the commutation relations are these, and we then constructed a set of eigenvectors, or the set of eigenvectors of our early Hamiltonian, where n in is the nth eigenstate of the early Hamiltonian, and En in is the nth eigenvalue. The eigenvalues are, of course, just these, as is always the case for harmonic oscillators. The eigenstates n in can be expressed in terms of the ground state of that Hamiltonian by applying the A-Dagger operator n times and multiplying with a suitable normalization factor. It turns out that the set of so defined vectors is not only orthonormal, but it's also complete. So it's the Hilbert basis of the Hilbert space of that harmonic oscillator. Now, at late times, the Hamiltonian has become a different operator, but it's again constant. Now, it's this operator, and we can calculate now its eigenvectors. Since it's a different operator, its eigenvectors are going to be different. But because the structure is so similar to that of the Hamiltonian at early times, we expect that we can go through basically the same kind of calculation again. And we can. We start with the fact that the A out and its adjoint operator have the usual commutation relations. So we can construct, just on the basis of this, the eigenbasis of our late Hamiltonian by the same method. Namely, there is a unique vector 0 out, which is annihilated by the A out operator. This is the 0 vector. And we define the set of vectors n out as being generated from this vector 0 out by applying the A-Dagger out operator n times and normalizing. The eigenvalues are going to be the same as before, because the overall structure is the same, we should expect the same eigenvalues. The eigenvalues En out are again omega n plus 1/2, as for any harmonic oscillator. But remember, the out Hamiltonian is of course not the same as the in Hamiltonian, so even though the eigenvalues coincide, the eigenvectors will not. After all, they are made out of different A-Dagger operators, the two Hamiltonians. So then, what we have is that the n out vectors are also normal, and again they form a Hilbert basis of our Hilbert space, of the same Hilbert space. So now we have constructed two bases of the same Hilbert space. Since they are bases, we can express any vector in these bases. In particular, we can express the basis vectors of one basis in terms of as a linear combination of the basis vectors of the other basis. And so the question arises, how are these two bases related? On general grounds, we can certainly say that each vector of the in basis is a linear combination of the eigenvectors of the Hamiltonian, the late Hamiltonians, that is to say, of the out bases. So clearly there must exist coefficients, let's call them lambda n, such that the linear combination of the n out basis vectors with these coefficients lambda n gives us the in basis vector, the zero in vector. Assume we knew those coefficients lambda n, then we could really get all of the complete map from the basis vectors, from the out basis vectors to the in basis vectors. And that's because we can generate all in basis vectors by just applying the A-in dagger operator on this. But the A-in dagger operator is easily expressed in terms of the A-out dagger operator. So we can act with it on here. So the key thing is to find out what these coefficients are, and that will induce automatically an entire map between the two basis vectors, between the two sets of basis vectors. That's our first occurrence of a so-called Bogoliubov transformation from one eigenbasis of a Hamiltonian to another. Imagine we had those coefficients lambda n. Then then it turns out that those coefficients lambda n have an immediate physical interpretation. Let's say our harmonic oscillator starts out in the state 0 in. So the harmonic oscillator before the driving was in its ground state. Because we are working in the Heisenberg picture, the state of the system is therefore 0 in, not only at the beginning, but always, forever. I mean, until the first measurement, and then the wave function collapses. So the state of the system starts out and always stays to be 0 in. Let's call that state gamma. It's a particular vector in the Hilbert space. Now let's assume that at a late time, after the force has finished acting, we measure the energy. So we measure that operator, that observable here. We will find an eigenvalue of a harmonic oscillator, En, and the corresponding eigenstate, and then the wave function collapses into that eigenstate. But what is the probability, or what's the probability amplitude for finding a particular energy value, En, when we perform that late measurement? Well, the probability amplitude for finding the state n out when we measure at a time t larger than capital T is given by the overlap of the state that the system is actually in and the state that we're looking for, as usual. So that's the probability amplitude for finding the state n out when the system has been prepared in the state gamma. So that's the probability amplitude, and the probability is just the modulus squared for that prepared state that we're looking for. If we calculate that, we find that this overlap, this probability amplitude, is the overlap between the n out state and the zero in state, because that's the state that we prepared our system in. So that's the overlap between n out and that linear combination. We are assuming here that we know what the lambda n's are. And then, because of the orthogonality of the various n out states, we have that in this whole sum, all terms go away, except for the term where m is equal to n. Therefore, this is lambda n. So, we found that lambda n has the interpretation that it is the probability amplitude for finding the nth excited state when, after the force has acted, when this harmonic oscillator was initially prepared in its ground state. Of course, in quantum field theory, this will then be interpreted as having found n particles being created when the system started out in the vacuum. N particles of a particular mode, of a particular mode oscillator. Okay, so the probability then is, of course, the modulus squared for the probability for finding the energy eigenstate at late times is, of course, just the modulus squared of that coefficient lambda n. In quantum field theory, this will be the probability for finding n particles after charges and currents described by a function j of x and t excited the vacuum. And not just n particles arbitrarily, but n particles of a momentum, of the momentum, of the mode oscillator that we happen to look at. We can do this calculation for every mode oscillator, for every Fourier mode separately. Now, let's calculate lambda n. In the mathematical tradition, I'll just give you the solution right away, and then we prove it afterwards. Let's do it this way, round for once. So the proposition is that lambda n is given by this expression here. Notice that this piece does not depend on n. You can view it as a normalization factor. But this piece depends on n, and we recognize our constant J0 here. So let's prove this. So the claim is that the in-ground state is this linear combination of the out eigenvectors of the Hamiltonian. Right, so these are the lambda n coefficients. That's the claim. There are two things to check. One is that this expression here really is the A-in, the zero-in vector. And we check that by checking that A-in annihilates that vector. Okay, because there's only one unique vector that is annihilated by A-in up to a phase. And secondly, we have to check that this vector is not only obeying that condition of being annihilated by A-in, we also have to check that it is normalized to length 1. Because 0-in is defined as a vector of length 1. Okay, so we have to show that when we apply A-in on all of this, then it's annihilated, we get 0. But when we apply A-in on this, well, then we have A-in acting on out vectors. That's not obvious what that will do. So we use the fact that A-out can be expressed as A-in plus J0. And then this is just a multiple of the identity operator. And that acts in a known way on the n-out vectors. So what we need to check is that A-in on 0-in is vanishing, which is to say that A-out minus J0 on 0-in is vanishing. Let's see if that works out. So we have to show that A-in, this is A-in, acting on that thing is equal to 0. What is it? Well, we carry forward that coefficient here, and we have this bracket act over here. And then these coefficients here will combine with the coefficients that arise when we express n out in terms of 0 out. So n out, if you remember, can be written as a dagger out to the nth power normalized with 1 over square root of n factorial. This is just n out. And this coefficient here combines with the normalization coefficient of n out to just give us 1 over n factorial. But that's nice because it means that we just get an exponential here. J naught to the power n, 1 over n factorial, and a dagger out to the power n. That is an exponential. Okay, so we carry forward that normalization factor, carry forward this, and then all of this is simply J naught times a dagger to the power n over n factorial, summed over n. This is this exponential here. So the expressions that we get are a out acting on e to the power of j naught a dagger minus a j naught times that. And then let us rewrite this expression by basically commuting, using the commutation relations to commute the a through all those powers of a dagger so that the a is on the right hand side. We do that because once the a is acting on the right hand side, it will act on 0 out, and that term will go away. So what we do for that purpose is that we rewrite this term, which we can view as something times something else, so some a times b. We write a times b as the commutator of a and b plus b times a. Right? That's a trivial statement here, if you just write out what the commutator is. So let's do that. We write out the commutator, we write this as the commutator plus the two things the other way around. Okay, so we get the commutator of a out and e to the power of j naught a dagger out plus these two things the other way around. That's this term here. And that term was just carried forward. Now at this point, we need to evaluate what the commutator is between a and e to the power of a dagger. It turns out that when you take the commutator of a with a function of a dagger, you are in effect differentiating that function with respect to a dagger. Let me show you how that comes about. In principle, I'd like you to do this as an exercise. So the claim is that the commutator between a out and this exponential here is j naught e to the power j naught a dagger. If you look at it naively, it is as if you just differentiated that term here with respect to a dagger. Because you just get a j naught down, right? And that is not a coincidence. So the exercise is to prove, using the fact that a dagger has this commutation relation, that the commutator between a and any function f of a dagger, at least any function f of a dagger that can be expanded as a power series, is the derivative of that function of a dagger. And here's a hint. In order to show that, start with this. The commutator of a and a dagger is 1, the commutator of a and a dagger squared is 2 a dagger. You see, it's like taking the derivative. Commutator of a with a to the third power is 3a squared. And then, for example, by induction, you can prove that the commutator of a with a dagger to the power n is n times a dagger to the power n minus 1. And that's really all you need to show that indeed the commutator of A with any function of A dagger is giving you the derivative with respect to A dagger. And then a special case of that is this equation here, which we need up here. So in our calculation, the next step that we take is that we replace that commutator by the derivative with respect to A dagger, and that is just giving us a J naught times this exponential. But we also have a minus J naught times that exponential. So we get this expression here, which is vanishing. And we also have that BA term, which is this times that, but the A out acting on the zero out vector is vanishing too. So the whole thing vanishes, and indeed that's zero. So what we've shown is that the claim, we've proved now that this could be right, because A in acting on that expression is really zero. What we still have to show is that this vector is really normalized, so that this is the right prefactor for that. I leave it to you to prove the normalization of that vector. Now, quantum field theory. So far, this was just an individual harmonic oscillator driven externally. Remember the picture of the lake, some waves on it. And we could put a piece of cork in that lake. And when we do, then this piece of cork will bob up and down. But we could also attach a cord, a string to that piece of cork, and then use it to pull it through the water. See, in this case, the cork is not just seeing what is going on in the lake. It's not just an observer of what's going on in the lake. It's not just serving as a detector of waves, detecting by going up and down. No, if you pull on this thing and you pull it through the water, then just like a duck that cruises through the lake, it will make waves. It will not just detect them, it will also make them. Very much like a charge that goes through the vacuum. A charge can be used as a detector of waves. As a wave, electromagnetic wave, goes over a charge, it will shake the charge. Just like the cork will be shaken by waves that pass over it. But as you move around the charge, it will also create waves. There's just one key difference, which is that in water, no, it would be confusing. I will not say that. Okay. Right. So in the electromagnetic case, the analog of the cork could be a charge that you place in the vacuum. And these would be typical vacuum fluctuations, similar to what might be going on in the background in a lake. And so let's say you have a positron there, and that positron is exposed to the quantum field. As such, if there's an electromagnetic wave washing over it, the positron is going to be moved back and forth. But also, you could choose to accelerate that positron. For example, you could have here a piece of metal, put a lot of electrons on that piece of metal, they will attract the positron will accelerate towards that. And while it does so, it's similar to this cork being pulled, and this will create waves now. So now this electron is no longer just a mere observer, a mere detector of what's going on in the field, it is creating waves as well. How do we describe that? Well, we now have the tools for this. Let's say we take this Hamiltonian. Up until here, this is just the Hamiltonian of the free Klein-Gordon field. This is the p squared over 2, and that's our omega squared q squared, omega squared half q squared term, but for the quantum field. if you rewrite p as phi dot, do an integration by parts, then you can have a second time derivative in this, and then combine it with that to obtain a D'Alembert operator. So here's the Hamiltonian of a free field up until here, and this gives us an opportunity to introduce a driving force for the harmonic oscillators of the quantum field. The J of x and t here plays the role of the charges and the currents. This is a simplified model of what is really going on, for example, in electromagnetism, where you would have the action here of the electromagnetic field, which is essentially E vector squared with B vector squared. The electric and the magnetic fields are playing the roles of the P squared and the phi squared. And here you would have a term that couples a background current of charges to the electromagnetic field A. But electromagnetism is a little more tedious, and for the purposes that we have in mind here, we don't need to go into the details of it. And with electromagnetism, you basically have to worry about the vectorial structure of the E fields and the B fields and the A fields and the currents. But we can just as well see those phenomena with scalar quantities as well. Okay, so an example interpretation is this. Phi may be viewed as a slightly simplified version of the quantum electromagnetic field, and J could be viewed as a simplified version of a given classical electrical charge and current density function. Notice that phi and pi have hats on them, so they are operator-valued fields. They are going to be quantized, but the J of x and t is just a classical background. It's a classical charge. Or classical charges, classical currents. And we might ask, if you take the quantum electromagnetic field and you tickle it with classical charges and currents, how many photons are you going to create? How much are you going to excite the quantum electromagnetic modes? That's something we can now answer with our study of harmonic oscillators, just above. So for example, we might take for this J of x and t, just one particle, just like one positron or so, and have it cruise around. So J of x and t would be a charge distribution which is, for example, q times the delta function of x minus x tilde of t, where x tilde of t is the path that our positron is taking. It's a classical charge that's moving around, and we want to know how is that classical charge creating electromagnetic excitations, photons. But of course, it doesn't have to be just one particle. You can have a current distribution of any complicated shape. So we could look at in and out periods. Let's say this positron is doing its job only for a finite amount of time. So we consider the case where the charges are absent at all times other than the time interval from 0 to capital T, just like with the harmonic oscillators before. Then, in principle, it suffices to study the periods of before the charges acted and after the charges acted. In those, not during the time that the charge was acting. In those early and late periods of time, the charges are absent, and therefore the Hamiltonian is in both cases simply the free driven harmonic oscillator, and the free undriven harmonic oscillator. So what we need to solve then is just the free quantum field theory, where we have the Klein-Gordon equation here, the commutation relation, and we went through this earlier. In order to solve these, it's convenient to employ a Fourier transform, because then this derivative becomes an ordinary multiplication operator. And that will decouple these harmonic oscillator equations. Remember, at every x we have a harmonic oscillator equation here, except that the Laplacian couples neighboring harmonic oscillators. By going to the Fourier transform, these derivatives become multiplication operators, and then we have truly uncoupled harmonic oscillators. So here's the Fourier transform that accomplishes that. After that Fourier transform, the new variables are the phi hat k, and their Klein-Gordon equation is this one. Laplacian became k squared. And obviously this is just a harmonic oscillator whose frequency squared is k squared plus m squared. The canonical commutation relations between the phi k and the pi k prime are given by this. Remember that notorious plus sign there. The hermiticity condition on our classically real quantum self-adjoint phi field is this one, which after Fourier transform became that condition here. We use the solution strategy to Fock in complete analogy to how we did it for the individual harmonic oscillator. So at early times, we can work this way. We introduce, just like in the quantum mechanical case, where we introduced a variable a of t, which is given by this linear combination of q and p of t, where, remember, these were fine-tuned. These coefficients were fine-tuned with two conditions. First is that a and a dagger commute into 1. And the second was that these coefficients are fine-tuned such that the harmonic oscillator with frequency omega takes a particularly simple form because it has no a dagger squared, no a squared terms. Then in quantum field theory now we imitate this completely by writing this expression here. So you see that it's the same prefactors there, they will accomplish the same thing. And the q, instead of the q hat, we now have a phi k, instead of the pi, we have a pi k. Notice that it's quite interesting that we get away with this, because here, this one in quantum mechanics, this is self-adjoint, that's self-adjoint. This is not self-adjoint, that is not self-adjoint. But we still get away with it because there is no self-adjointness or otherwise condition on the AK. The AK is not equal to its dagger, nor is it the negative of it or anything like that. So we actually get away with this very simple analogy there, as we will find out. I mean, this is nothing to derive, it's the definition, right? That's why there's this column before the equality sign. And then let's see what we get. Well, we get that, just like in quantum mechanics, the equation of motion was this one. In quantum field theory, for every mode oscillator, for every Fourier component, the equation of motion is this one. And the commutator turns out to be this one, between the A and the A dagger. It's the correct commutator for the same reason that it worked out in quantum mechanics. Remember that this is the equation of motion in the absence of a driving force. So when there's no positron whizzing around or any other charges going around. So then the solution in quantum mechanics was that A of t is A in times that time dependence. In quantum field theory, the AK of t is the A in k times that. So the only thing to remember here is that in quantum field theory, we're dealing with infinitely many harmonic oscillators at a time, and each one obeys such an equation. And we have infinitely many A and A dagger operators, one for every choice of k. So we have explicitly now A of t, or all of the AK of t, which means that we can go back and write down the solutions for the original problem, for the q and the p, for the phi and the pi. So in quantum mechanics, we can now, for example, re-express the q of t in terms of the A of t and a dagger of t in this way. In quantum field theory too, we can now re-express, express the phi hat k of t in this way. by writing down the solution for A in of t and A in dagger of t. Okay, so now we have the explicit time evolution of all the mode oscillators. Let's go all the way and solve the original problem, which was to find phi hat of x and t. All we have to do is Fourier transform this back into the position domain. When we do this, we obtain that phi hat of x and t is given by this long expression here. The difference is only that we Fourier transformed from k space to x space. So this then is a very important equation that we will need later on in this course. It's the solution for the Klein-Gordon problem for all space and time as long as the system is undisturbed. Okay, so notice here A in operator times this time-dependent factor, and you can see the covariance of it here. And here the A dagger, and again this covariant time and space-dependent phase. How about the Hilbert space of states for the quantum field theory? Well, analogous to the case of quantum mechanics, there is a vector 0 in the Hilbert space of the quantum field theory, which is annihilated by all of the A in operators. So technically, the zero in vector of the quantum field theory is the infinite tensor product of the zero in vectors of all of the mode oscillators. So it's really 0 in for one k, tensor 0 in for the other k, etc. It's infinite tensor product of the ground states of all of those harmonic oscillators.
Is there any subtleties because that's a natural cross product?
Because it's a what cross product?
Like, are we limiting ourselves to a finite number of k? Or like
ideally we would use a finite number. Less ideally, it would be an infinite but countable number. Realistically, it's actually uncountably many, and that is very much a subtlety, yes. And in practice, we will have to regulate this. Yes. So the Hamiltonian now takes which form? Well, the Hamiltonian in the Fourier domain is given by this expression here. It's basically the p squared over 2 plus omega squared half, and then the q squared. But for every mode. So you see this is just a sum, or really an integral, over the Hamiltonians of all the mode harmonic oscillators. For every k, we have the Hamiltonian of an ordinary harmonic oscillator. Now, let's write this out in terms of the A and A daggers, and we will find that there is a problem. If we write this in terms of the A and A daggers, in principle it becomes very simple, because remember that each harmonic oscillator simply becomes of the kind omega k, and then A dagger A plus 1/2. Except in quantum field theory, it's actually A dagger A plus 1/2 Dirac delta of 0. And the reason is, I think I just, here it is. In quantum field theory, the commutator between the A and the A dagger operators is the Dirac delta of k minus k prime, which is good. It's a minus here. We constructed it nicely, so it's a minus, not a plus. But it's a Dirac delta, not a Kronecker delta. And in the harmonic oscillator case, remember that you get that the spectrum is n plus 1/2, h bar omega n plus 1/2. Well, n plus 1/2 times the Kronecker delta evaluated at its peak. But this is a Dirac delta. So what we obtain here is 1/2 Dirac delta to the third power of 0. But the Dirac delta evaluated at the point where it peaks is of course not a number. If anything, it should be infinite, but it's not even infinite, it's just ill-defined. This is what is called, this infinity of, the infinity of this term is called an infrared divergence. It arises only because we chose to work in R3. If we put our system into a large enough box, so we do the infrared regularization of using a box, then remember that we no longer have a continuum of k's, we have only a countable number of k's. The k's take only discrete values. And in that case, we recover the situation with a Kronecker delta here. It's Kronecker delta of k and k, so that becomes just a 1 again. So that's very nice. This means that quantum field theory can be much more regular. It will be much more regular. We don't have this infinite energy here if we do it in a box. In practice, it looks like this. In a box, we have that the Hamiltonian is L to the power of minus 3/2 times the sum over all k, instead of the integral, the sum of them, and you can look it up in the earlier lectures why this is the right normalization factor in front of that integral, in front of that sum. Basically, see, this sum must become a Riemann sum if you take the limit again to the integral. Yeah, and then we have here the 1/2. Okay, so each harmonic oscillator has now only a finite energy. Trouble is that that's still divergent, but now for a different reason. Now this is divergent, the whole sum is divergent, because never mind what this is doing. What we have here is 1/2 times omega k, summed over all k. And there are infinitely many k. Which means that this sum over all k, omega k times 1/2, is definitely infinite. Now, there would be a way out if the omega k were to diminish and eventually go to 0 fast enough. Well, then this series, sum over all k, omega k times 1/2, has a chance of being convergent. But that's not what we expect, because omega k is actually the square root of k squared plus m squared, which is to say that omega k grows linearly with k. So it actually gets worse as you go to larger and larger k values. So that's a pretty bad divergence here, and that's an ultraviolet divergence. It turns out that this is a much more serious thing. We can't just, this will not be helped by going to a box. We already went to a box. This has to do with the short distance structure of the quantum field theory. That's why, or the short wavelength structure, that's why it's called ultraviolet problem, ultraviolet divergency. If, for example, we assume that there are no wavelengths shorter than a certain wavelength, then this means that we are not summing over k's larger than a particular wave vector k, of particular length k max. So that would come out finite in this case. So the reason why this is a divergence is that we insist on summing over all k values, which means arbitrarily small wavelengths. We do not expect that we really have to sum over all k, because we expect that it doesn't make sense to consider wavelengths shorter than the Planck length, because quantum gravity will induce quantum fluctuations of space-time that make the very notion of such a thing impossible to make concrete operationally. We don't know how to describe even in principle a wave that would have a wavelength shorter than the Planck length. But nobody really knows what to replace that with. What really happens to this sum as the k values approach the Planck wavelength? We don't know. But in any case, this is a strong indication that something has to give, because otherwise this Hamiltonian comes out infinite right away, independent of this. Now, for ordinary quantum mechanics, as long as quantum theory, as long as gravity is not involved, we can sweep this under the rug. For example, for the purpose of particle physics, as it is done at CERN, you would sweep this term under the rug by saying, well, yeah, it's infinite, but it's a multiple of the identity operator. And therefore, when the Hamiltonian generates dynamics by commuting with observables, that contribution doesn't matter. It's just the identity. So it commutes with every operator. So this term is not going to affect the dynamics of any observable. With gravity it's different though, because the energy will enter into the energy momentum tensor which curves space. And so we cannot just sweep it under the rug. Okay, so now after the driving ends, the time evolution of the A operator is given by this, e to the power minus I omega kt, A out k. Just the same as we had it with the individual harmonic oscillator. And the relationship between the A out operators and the A in operators is mode by mode, because all those modes are independent. The different k values don't talk to each other. There's nothing in the Klein-Gordon equation or the commutation relations or anything else that relates different k's to each other. We have that A out k is A in k plus J naught k, where J naught k is just the windowed Fourier transform of the driving current. So as before, the impact of the driving, in this case the charge and the current, the amount of impact it has to do with the amount of frequency that J has in the amount of frequency component that the driving current has at the value of the frequency of the mode that we are considering at the moment. So every driving will be resonant with some modes and off-resonant with other modes. So just remember that Jk of t is the Fourier transform, the temporal Fourier transform. Jk naught is the temporal Fourier transform of Jk in that time window from 0 to t. So now, knowing all of these things, then the relationship between the out and the in operators with J naught, and J naught can be calculated explicitly. So you have some current distribution through space and time, and then you Fourier transform it in space, you get the Jk of t coefficients, and then you take the windowed Fourier transform in this way, and you get your J naught coefficient for every Fourier mode, and so you can then calculate how much every Fourier mode gets excited. So to this end, we again generate the basis, the out basis n out, with this defining equation, and we can then calculate the overlap between the out vectors and the in vector, the zero in vector, and that's going to give us the probability amplitude and the probability for finding n particles of momentum k being created if the quantum field started out in its ground state, in its vacuum state, and those charges j of x and t were operating for a while. Now remember the picture that we had in mind here. We said that on one hand, we have, in the picture of the water, we have this cork. And if we pull it, it's going to create waves. And here we calculated the analog of that for quantum fields. We took a charge, for example, a positron, and we pull it through the vacuum, for example, by having it accelerate towards some charged plate. And then this positron too will generate electromagnetic waves. The motion of our positron is described by a function j of x and t. And by Fourier transforming it in space, we get jk of t. And then from the jk of t, we can calculate for every Fourier mode what its j naught of k is. And that will tell us how many photons of momentum k are being generated by this process of the E plus moving around. So our next, well, let me just say, are there any questions about this before we move on? Would you all know how to calculate how many Klein-Gordon particles are being generated of momentum such and such, given that there are certain charges and currents around given by J of x and t? Okay? Good. Let's upgrade. Let's upgrade this picture. Let us give J of x and t now its own dynamics. And by that, I mean, remember the cork had two functions. If you put a cork into the water, then it will bob up and down, and as such it will act as a detector of waves in the water. You can find out what the wave situation is at the location of the cork at any time. The second role that this cork plays is that by pulling it, we can actually create waves. In other words, corks can communicate with each other. You can use one of those corks somewhere and another one over there. You can just have both of them observe the local wave field, but you can also move around one of the corks, and that will be registered a little later by the other cork. Similarly with charges, of course, you can have two charges. If you move one, you will create electromagnetic fields that will eventually shake the other. But now let's upgrade this. A single positron doesn't have internal degrees of freedom. You can't excite a positron. Now, a cork, too, in principle doesn't have internal degrees of freedom. You can't excite a piece of cork. But let's rig it so that you can do it. So what I've done with this piece of cork is that I've cut it here. Okay? So I cut here through this piece of cork and put a spring there to link the upper and lower part of the cork. Now, this piece of cork has its own degrees of freedom, its own internal degrees of freedom. There's a harmonic oscillator now in this cork. It doesn't even have to be harmonic. It's just some degree of freedom. This thing can now vibrate. And what that means is that the role of the cork now becomes more sophisticated. If you put this piece of cork into the water, then let's just have it sit there for a moment. Then as waves go through, those waves will in a subtle way excite those vibrational degrees of freedom of the cork. In other words, by observing the internal excitations of the cork, we can learn about the wave field where the cork is. Similarly, we can upgrade the picture of the positron. Instead of using a positron and placing it there as a detector of what the waves are doing, let us put an atom there. Now the atom is a more sophisticated detector than the positron was. You see, the issue with the positron was that if you put a positron somewhere there and the waves go through, then the positron will sure recognize the wave, but it will do so by being moved around, which is kind of defeating our purpose, because we wanted to know what the wave field is at a particular location. But now this positron moves around. If the wave is strong enough, it will kick the positron all over the place. Different with the atom. If you put an atom in there and task it with detecting the electromagnetic field, it can do it in a much more sophisticated way. You could imagine this atom as being really heavy as compared to the energies available from the field. And then the atom could detect the presence of electromagnetic waves washing over it by being excited. Very similar to the cork. The cork is sitting somewhere in there, a wave field is going over it, and the cork starts internal oscillations as it happens. So here too, you put the atom somewhere into the electromagnetic field, and let's say you keep observing its excitation state. If the atom just stays in the ground state, you conclude, well, there may have been electromagnetic fields, but they sure weren't strong. If, however, the atom actually gets excited, let's say it's being lifted from its ground state to the first excited state, then you know that the atom must have absorbed from the electromagnetic field a photon of a particular energy. So you know something about the wave field that was going around. So it's a destructive measurement. The atom is going to measure something about the electromagnetic field while changing the electromagnetic field, for example, by absorbing photons. But never mind. It's a measurement, all right. So that's one of the tasks that that this more sophisticated setup can serve. The quark can serve as a more sophisticated detector now of the wave field, and so does the atom. It serves as a more sophisticated detector of the wave field. But secondly, these things are not only detecting, they can also emit, right? Because they're charges again. You can pull on this thing, it will move through the water, creating waves, in the process also getting excited. See, if this water was completely still, and you started ripping this thing and moving it across the water, you would expect that this thing would start oscillating. Not necessarily if you pull it at constant speed, right? Then you would probably just have a constant distance there. But as soon as you start accelerating this thing around, you would expect that this quark starts internal excitations. Okay? So similarly here, for the quantum field, the atom could be placed in there and merely serve as a detector of an electromagnetic field. But you could also whisk it around. Again, make it charged. Put something that's charged there, and the atom will accelerate towards that. It's like dragging the cork through the water. Now you're dragging a charged atom, an ion, through the vacuum. And again, you would expect that it creates waves. Sure it does. A single positron would already do that. A charged atom will do that too. But more than that, you would expect that it gets excited too in the process. Just like the cork gets excited if you pull on it in an accelerated fashion, you would expect that it starts to oscillate. So here too, we might expect that if you accelerate an atom, then it will create electromagnetic waves, but also it might get excited. Now that is curious. That is a curious phenomenon because there is the possibility to define what a particle is using an atom as a detector. In fact, it's probably the best way we have to identify what a particle is. The idea goes back to Unruh and DeWitt, and they said it's all fine to say that when a quantum field's mode oscillator is in its fifth excited state, that this describes 5 particles with a momentum k of that mode oscillator. How do we know? How do we know that this is really how we should interpret these things? It's true that lifting this harmonic oscillator of a mode from one energy level to the next, if the mode oscillator has wave vector k, then the energy it takes to increase the excitation by 1 is exactly square root of m squared plus k squared, which is the energy it takes to produce a particle of that momentum. That is corroborating evidence that we might be up to something good here if we interpret excitations of mode oscillators as particles of particular momenta. But then you can criticize and say, look, but these would be particles with a fixed momentum. When we actually find a particle, it makes a click somewhere in a detector. That's localized. How do we localize a particle in quantum field theory? This idea has been proposed as the next best thing. There is a compromise to be done here, because we're treating the atom in first quantization and the field in second quantization. But other than that, it's probably as good as it gets to ever identifying the localization of particles in quantum field theory. So what Anwar and David said is that instead of, or maybe better, on top of, or alternatively to, identifying particles as excitations of mode oscillators, let us identify particles as whatever particle detectors detect. So the idea is that we use this as a fundamental principle. We take a quantum system that can be excited, such as an atom or a molecule or whatever small system you might have, some localized system, treat it with first quantization, put it into a quantum field, and whenever that thing clicks, whenever that thing gets excited, we interpret this as the absorption of a particle from the field. Whenever it gets de-excited, we interpret this as the emission of a particle from the field, into the field. So this would then serve as the definition of what a particle is. A particle is whatever makes a detector click. I mean, change its excitation state. And because these guys are localized, we get local information. It's a description of the local clicking of detectors. But remember what we just said earlier. We expect that when we pull around this cork through the water, then not only will it make waves, no, it might also get excited. Not if you pull it at constant velocity, but if you pull it in an accelerated way, you would expect that there's some oscillations going to get started there. And so similarly with an atom, you might expect that if it's just inertially moving around, it might not on its own get excited. In fact, that would be weird, right? An atom that's moving inertially would suddenly get excited out of the vacuum. That would be very weird. But what if you take an atom and you accelerate it through the vacuum? By this analogy, we might expect that it not only creates electromagnetic waves, but also gets excited itself. But that would mean that it detects particles by the interpretation that we just developed earlier, which would mean that an accelerated detector sees particles where nobody else sees them. Anybody who is inertial doesn't see particles, but an accelerated detector will see particles. That is the famous Unruh effect, and we will cover it in the next lecture. It's the effect that accelerated detectors see particles. Or, to say it most carefully, accelerated detectors will click. We will actually describe these things in a simplified fashion, but you could do it for full-fledged quantum electrodynamics or QCD even if you want, or the weak interaction. We will just do the Klein-Gordon field, and here's roughly how we will do it. Or not roughly, but exactly how we will do it. So here's the Hamiltonian that we considered earlier. We have the Hamiltonian of the Klein-Gordon field, and then we had a positron, or generally a classical current, described by the function j of x and t, and coupled it to the Klein-Gordon field phi hat. And remember, we studied today how, given that classical charge and current, for example, charges and currents that run up and down an antenna, you can calculate how many photons of particular momentum are being created. Now we do the upgrade. We do the upgrade by cutting the cork, or by replacing the positron by an atom. In each case, giving the object an internal degree of freedom. So we do this upgrade in the following way. We now say that the Hamiltonian is given by a Hamiltonian which consists of the Hamiltonian of the electromagnetic or Klein-Gordon field. This is the Hamiltonian. Tensor the identity operator on the Hilbert space of the atom, like the Hilbert space of the cork. So it's acting as the identity on the Hilbert space of the atom, tensor the usual Klein-Gordon Hamiltonian on the field, plus this interaction Hamiltonian. It's now a J hat. It's now an operator that acts It's space and time dependent, and that acts on the Hilbert space of the atom or molecule, and that's the field again. So in principle, all we did is we put a hat on there. But of course, that required us to introduce a new Hilbert space, because it's no longer just classical. And in the simplest case, this J hat of x and t could be of this form. It's some Q hat of t, which is some operator in the Hilbert, that acts in the Hilbert space of the atom, multiplied with the Dirac delta that peaks at the location of the atom. So this is a Dirac delta in 3 space, and it peaks, it has a contribution only when x equal to x tilde of t, where x tilde of t is the path that our atom is taking. So this is, of course, a simplified description here, because the atom is here described as point-like with the Dirac delta. And often it is better to regulate that and, for example, make this a Gaussian distribution of the charge of an atom, or in fact use the actual charge distribution of an atom, use the wave function of the lowest Bohr orbit, for example, and something like that. But in practice, we may be working with wavelengths that are much larger than the size of the atom, and so this is a good approximation to work with. So our Hilbert space is then the tensor product of the Hilbert space of the atom and the tensor product of the quantum field. The atom is described here in first quantization. We will work with the position and momentum operators of the electron around the nucleus, or the electrons around the nucleus. And the Hilbert space of the field is of the second quantize, of the quantum field theory of the quantum field. This is, of course, a mixed situation here. Ideally, we would like to do everything in second quantization, but it would be extremely tedious. You could do that. You can describe an atom with quantum field theory, of course, but it's not easy to describe bound states in quantum field theory. Even the bound state of a positron and an electron is already difficult to describe in quantum field theory. And then the simplest atom, the hydrogen atom, is already very complicated, because the proton is made out of quarks, and it would be just nightmarish, and you don't really gain much by going to second quantization. So we'll do the atom in first quantization. We will also use a simplified notation, namely, instead of spelling out those tensor products, we will use the notation that virtually everybody in the field is using, which is to just not mention those tensor products. Of course they are there, but you're not writing them out. So then one tensor, this operator, just becomes this in that notation. It's really this stuff, tensor 1, or one tensor, this stuff. And then here also this tensor product is of course there, but it's not spelled out. Yeah?
I'm a bit confused, I guess, for a long time. Where do we put the limit? Where do we say, okay, first quantization is enough? So where can we decide where to use second quantization or first quantization?
Yeah. The limit is twofold. Remember the reasons why we went from first quantization to second quantization. One was relativity, and the second was particle creation, particle annihilation. Now, for a hydrogen atom, you can incorporate relativity to some extent without having to go to second quantization. Now, for the hydrogen atom, if you want very high accuracy, then you need second quantization. Namely, you need to take into account that as an electron is bound by a proton, this electron can emit a photon and then reabsorb it. And the next order is that it emits a photon, which splits into an electron-positron pair, and then that collapses into a photon again, gets reabsorbed, and so on. These processes can be and should be taken into account for the hydrogen atom. And in this way, you can achieve a match between experiments and theory of like 10, 12 digits behind the comma. For our purposes, though, particle creation within the atom is not going to be important. Basically because when we want to know, are there photons present in the field, by the atom absorbing them and getting excited, then it's not so, we're usually not really concerned with the exact wavelength of the photons that are being absorbed. So as long as we don't want to do super high accuracy measurements of the frequency, we don't really need to worry about the second quantization.
So basically, if our system creates or annihilates particles and it is relativistic, we might go to a second quantization picture.
Yes.
So the argument would be, if I want to describe the hydrogen atom,
Yeah.
first approximation,
Yeah.
I'm not that concerned about particles getting self-created within the
Yes.
system.
Yes, that's right.
So I can say, okay, I'm safe in the first quantization.
Yes, that's right. Where it would really fail is if you wanted to use one of those hydrogen atom detectors or general atom detectors, let's say, at CERN in the middle of those collisions, because it would be just threaded, right? The particles that would go along, even the photons, would be so powerful that they would immediately ionize that atom.
Okay.
Yes, so there you can do it. Yeah. So if you wanted to apply the Andrew de Witt detector model to extremely high energetic processes in quantum field theory, then you would have to postulate the existence of atoms that are sufficiently heavy, sufficiently tightly bound, that they could withstand those ultraviolet photons coming along. Which, as far as we know, there are no such atoms, but as a matter of principle.
Could you use like the proton and excited states?
In principle, yeah. Could be any bound system that you can use for that. Yeah, it doesn't have to be an atom. Yes, or a meson, sure, can do that. Okay, so we will do both. We will view the charged systems. So, a quark is a charged system because it can detect and make waves. And similarly, the charges in an atom, or if the atom as a whole is already charged, you need charges there in order to actually see the electromagnetic field. A neutral particle like a neutrino could not be used to detect electromagnetic waves. Again, we will use this both as an emitter and as a detector of electromagnetic radiation. And with all this, we will keep in mind the definition. It goes back to Andrew and de Witt, that a particle, such as a photon, is what a particle detector, such as an atom, can detect by getting excited. So, I already said it, but the slides were anticipating that I would say that much later. If you have a charged Andrew de Witt detector or emitter, like such an ion, and you accelerate it, let's say because of some charges there, then it would create electromagnetic waves, but it would also get excited. And this phenomenon, the fact that an accelerated charge is not only creating electromagnetic fields, but is also itself being excited by the acceleration process. That is the Andrew effect. It's saying that if we go by that definition, namely that the particle is what a particle detector detects by getting excited, then we have to say that an accelerated observer will see particles just because he or she is accelerated, whereas an inertial observer may not see particles in the vacuum state. You can even have the opposite. You can even have a state in which inertial observers will see particles. But if you arrange it in a fine-tuned way, you could have that a particular accelerated observer will not see particles. because the detector will not click in this case. Now, by the by the equivalence principle, this is of course related to gravity and the ability of gravity to make detectors click. And so, as we will see later on, this will also be related then to Hawking radiation. But you see, in principle, it's not mysterious. You can view it as going back to the same reason for why a piece of cork that has an internal degree of freedom, when accelerated through water, would start getting excited as well. Okay, so that's it for today. Any questions?
So isn't there a little bit of danger here in this definition? Because, so we say a particle is something that will make a detector click, but the way we would check to see if the detector has clicked is, say, look for an emission after the fact or something like that, because mathematically we can see, oh, okay, it's gone from one excitation to another.
Yeah.
But if we're just observing the system, we don't know it's been excited until something else has interacted with that excited state.
So you're saying we're pushing the can just further down the road in this way?
Well, maybe not pushing the can, but I'm not sure if it's entirely independent.
Okay, let me answer this then. When you observe us, are you doing it the unlimited way? Basically, you have atoms in your retina that will do just that, and they will get excited and they will hand over that excitation then eventually to your nervous system and so on, right? So what that would mean is this calculation is that if you are accelerated and you're sitting there in your spaceship, your retina will see particles, right? So in that sense, it's pretty real.
Yeah.
Of course, while at the same time, it's true that, inertial observers think, what is the vacuum? What do you see there?
Has this been experimentally detected? Have people accelerated things and seen parts related?
The clean number effect, as I demonstrated it here, no, has not been detected, but it would be very exciting and people are really trying hard to do it. Because it is closely connected to Hawking radiation. Not the same thing at all, but it's closely related to it. And there's also a fine interplay where they can actually sort of compensate for each other and they annihilate each other. So it's one of the big challenges that experimentalists are after. As far as I know, the closest that people have come to that is it's nothing really exactly like that, but imagine that instead of having a charge that you're accelerating around, you could have an interface between two dielectrica that you could accelerate. So let's say you have, and you see, the interface, if it's one dielectric constant, it's one dielectric setup up until here, and then it becomes a different dielectric setup over there, then electromagnetic waves will in principle, you don't excite the vacuum just by having this. It will not just create photons. But if you move that transition, the location of that transition between the two dielectric regimes around very quickly in an accelerated fashion, then you can actually create photons. Predict a calculation similar to this one. In fact, similar to the calculation that we will do on Monday, next time. That we'll do on Friday. And that effect has been observed. At least, I'm not experimentalist, I don't know to what extent they really observed that particular effect. But the effort was this. Imagine you have a glass fiber and you let light go through that fiber. In principle, the fiber is homogeneous. Its dielectric properties don't change. So the light just moves. If you don't put a beam of light in there, there's not going to be one materializing out of nothing. It's just going to be empty and dark. Now, you can change the dielectric properties of that fiber. For example, you shine a laser not through it, but at it from the side. Shine a laser at the glass very strongly. So strongly that it will not linearly interact with the material, and thereby change its dielectric properties. This means that a beam of light that now goes through that fiber will suddenly, namely where the laser is hitting the glass, will suddenly find a different dielectric regime and will partially bounce back, for example. Now, imagine again that through this fiber you don't send light through it, but you have this beam from the side that is changing locally the dielectric properties of the glass, just by shining on it very, very strongly with high intensity. Now imagine that this laser is not hitting the glass at the constant location, but instead you make the location move. Okay, so you can very quickly change where the laser hits the glass fiber. And so in this way you can make that location where the dielectric regime is changing move along the fiber in principle very, very fast. You can also make it accelerate very fast. And the prediction would be that if you don't send photons through the fiber, but you make its dielectric properties move very quickly in an accelerated way, you would expect that photons get created in the fiber. And they say that, there are groups who say that they saw that.
I mean, the whole point of the Unruh effect is to show that virtual, vacuum fluctuation can become real, and the Chris Wilson's dynamic or Casimir effect kind of shows that, because it's just like changing boundary conditions in time with that boundary conditions that accelerate in time, right? So if you wiggle them, that's also acceleration.
Yeah.
So it's kind of been demonstrated that these vacuum fluctuations are out there, and you can
it's just that boundary conditions or dielectric constant change is not exactly the same as having a system with internal degrees of freedom moving around.
Mm.
So in that regard, it's different. There are basically two ways to look at the Unruh effect. And one way is the way that I presented here today. And another way is to say that we do not use Unruh detectors. We don't put a quark or an atom in this field, but instead we assume that there is an observer that's being accelerated, and that observer is setting up his own coordinate system, and then is expanding the field in modes according to his own coordinate system that is accelerated. So that observer will have a new mode decomposition of the field. And then you can calculate the Bogoliubov transformation from the mode decomposition that an inertial observer would see to the mode decomposition that an accelerated observer will see, and check for excitation. You find excitation in this way. And we'll talk about that later as well. And that is closer related then to certain experiments that make the boundary conditions of modes vary in time.
When we've been doing this, we've been talking about flat Minkowski space, where you can define an accelerated observer easy, but in curved space, there's huge problems with doing some of these constructions. Like you can locally do it, but it's even then, that's sketchy.
Exactly, that is a big problem. As long as the wavelengths that you are considering are small compared to the curvature. In other words, if your space is flat, as far as the wavelengths are concerned that you're considering, then all of these things work just fine. But as soon as the curvature radius becomes of the size of the scale of the wavelengths that you're considering, then it's very, very difficult, and nobody really knows how to handle that.
Can't you write the Hamiltonian and Lagrangian and then go to a non-freely falling coordinate system, and then you'll get a mix of parametric driving from the curved space-time and then this sort of driving. I mean, if you write out in curved space-time, you have covariant derivatives, and then if you go to a non-vanishing Christoffel symbol frame, then you'll have Christoffel symbols. You'll have extra terms, and those will look like driving.
How do you define like an observer who's just an inertial observer?
Well, you can define
two different world lines, and you'd have to find you'd have to wait until they get local to be able to talk even and things.
Yeah, I mean there are many issues. Like two inertial observers may be accelerated relative to another, right? And also the calculation that we will do on Friday. In principle, we can do on curved space as well. However, for that you need to know what state the field is in. You see, coupling an atom to a field is a relatively straightforward task. You write down the interaction Hamiltonian, and the rest is just usual perturbation theory. But what state is the quantum field in? And that is not easy to determine. On a generic curved space-time that might be expanding somewhere, shrinking elsewhere, and then black holes forming, black holes evaporating. Nobody knows really what the state of the quantum field ought to be in this case. There's still a huge controversy. I mean, it's of course there are a lot of people who know, who believe they know what's going on. It's just that they don't agree with each other. Yeah, in fact, one feasible strategy is to elevate this approach to something fundamental and say that, well, whatever you choose for, by whichever method you try to identify what state the quantum field might be in, the detection of particles has to be plausible when you probe it with this.
In the picture that you presented us at the beginning of the discussion, that we put this system that has internal degrees of freedom, and then because it is accelerated, this system will get excited. So we'll see, okay, there are particles there. But in order to be accelerated, we need to include this wire with electrons there that actually, generate a force. So can we say, okay, these excitements that we're seeing are due to these extra particles that we needed to put there in order to accelerate the system?
Extra particles, I wouldn't say, but the extra energy. The energy for these excitations has to come from whatever the agent is that does the acceleration. There's no other source for it.
So I'm wondering, do you really need to change the state of your whole system for this vector to be accelerated? You need to put extra things there.
Yes, what we will do is we will consider a quantum system for the detector, for the atom, the quantum system of the electromagnetic field, but the agent that accelerates the detector system will be treated classically. You could make that more complicated, right? What you could do is you could describe the motion degree of freedom of the atom quantum mechanically. You could say, okay, it's an atom. It's moving with the center of mass that has a non-trivial commutation relation with its total momentum and so on. We will not do that. We will assume that the atom has a particular location at a particular time, which is prescribed classically. You can try to go beyond that, but it quickly gets complicated.
And maybe I'm a bit puzzled about the word effect, because it seems to me that if you put a system which internal degrees of freedom doesn't see this extra energy that is causing the acceleration, that system lives happily there, right? But if you put a positron and you have electrons, they will interact with each other. So it's not an effect, it's just like the interaction between, something needs to generate the force for this system to be accelerated.
Yes. Yeah, I mean, ultimately, you're right. Ultimately, you can decompose that entire picture here, this picture here. In principle, there is a second quantization view of this, where the electromagnetic field is described completely second quantized, the atom completely second quantized, and this too completely second quantized. You just have charges on metal, but that piece of metal might also be described by second quantization, and there will be virtual photons that accelerate this along, and so on. Yes, in principle, it's all a solution of quantum electrodynamics. Only, it's just that when we do that, quite apart from the technical difficulty of doing it, conceptually, we are back to square one because we still don't have a notion of particle at that point. See, if we stay completely within second quantization, then we are well within our rights because we assume that the standard model is all there is. And that's the second quantized theory, it's quantum field theory, right? So everything can be described by second quantization, even you and I, everything is second quantization. But then we still don't know how to localize particles or even what the particle is. And so it's a compromise to couple, to divide the world into a first quantized detector that interacts with the classical part, with the classical world on one hand, and with a second quantized field on the other hand. It's an artificial thing, but at the moment it's the best thing we have. I think it would be, it's not for lack of trying, people have tried to identify something like a position operator for particles in quantum field theory. But the conclusion seems to be in the community that, I mean, they've given up trying. You can't do it with the usual ideas. You have to come up with something outrageously new, probably, if you're able to succeed with coming up with something like a truly second quantized notion of localization of particles. So until that day, this is probably the best thing we have. We couple to a first quantized system, and then make use of the fact that with first quantized system we have complete control over the interpretation. See, there are no open questions about how to translate anything about the hydrogen atom into measurable quantities.
Okay.
This experiment you described with the boundary of the dielectric, and then this is kind of demonstrative of the Unruh effect, but not exactly. So what is that distinction? Why is that not exactly the Unruh effect? Because it's not.
Oh, because it's time-dependent boundary conditions instead of time-dependent detector. I mean, the closest you could come with that would be, let's say, it's a one-dimensional situation, and you put in a cavity a whole army of hydrogen atoms, one next to the other, right? And so there is this empty space where there is one dielectric regime, and then there is this space filled with hydrogen atoms. There's a different dielectric regimes because the hydrogen atoms are present there, right? And then you could move them around in an accelerated way, and that would start exciting them. I suppose that's how you could get similar. But generally, the idea. I mean,